Good afternoon, everyone. My name is Nick Valentino. I'm an academic counselor in the Hajim School, and I am your host for the Full Spectrum series. The Full Spectrum series is composed of introductory lectures from our Hajim faculty. This is an opportunity to ask Hajim faculty about their program, their research, and the types of challenges engineers in their field work to solve. Before we get into our program, I want to remind you that we're doing this again next week. With computer science with Dr. Shripati Pai. That is Friday, November 5th, 2 to 3. We will advertise this on our Facebook page. If you can't stay for the whole program, or if you're watching this later, these videos will be on the Hajim Facebook site. It'll also be on Instagram and YouTube. If you'd like the chance to win a prize, you can put your name in the chat or on the Facebook broadcast. And if you're a current or prospective student, if you're alum, faculty, staff, or any other part of the university community, you would be eligible. During this lecture, I will be monitoring the chat on Zoom and Facebook for questions, and we'll have time for questions at the end. Today, the session is presented by Dr. John Lambropoulos. Dr. Lambropoulos is a professor of both mechanical engineering and materials science. He's also won the Goergen Award for excellence in undergraduate teaching. So we're very excited to have you here, Dr. Lambropoulos. Thank you for doing this and for being here and being able to shed some more light on the world of mechanical engineering. So I will turn it over to you.
Great. Thank you very much, Nick. Again, welcome everybody on this short presentation as to what is mechanical engineering. This presentation, I originally prepared it a couple of months ago for prospective high school students who are thinking of possibly going into engineering, specifically mechanical engineering. But I think this will also serve as a good way of introducing mechanical engineering to first-year university students who may be wondering, what is mechanical engineering after all? So again, welcome everybody. So in summary, mechanical engineering covers a spectrum, if you like, of about 5 topics I've listed here. So structures, materials, fluids, energy, and power. So what I will do is I will go through each of these topics and see what comments one can make about the applicability of this to an undergraduate program. Okay. Oops. Mechanics and materials. The basic question is, why do structures fail? And this begs the question, what is the meaning of failure? So we need to understand under what conditions different structures would actually fail. For example, if I have a piece of chalk, I can break a piece of chalk very easily by simply bending it with my fingers, or I can think of a structure as being an aircraft. And an aircraft might have a catastrophic failure or progressive failure, and the scale doesn't really matter. It's just that we can look at things which are, let's say, handheld gadgets or a massive structure such as an aircraft. The other important topic is fluids, energy, and power. And this includes technologies such as propulsion, fuels, alternative energy, but more importantly, how we essentially extract power and how we transmit power and energy by using different types of fluids for different types of applications. A big overarching theme in mechanical engineering, just like in the other engineering disciplines, is the concept of engineering design. And this is essentially something that is not very familiar to many students who may have studied and taken STEM courses in high school or even at the university level. So engineering design is the kind of question that you set a given task or a given requirement so that another requirement is actually satisfied. So for example, how do you make a device or a structure so that the device can be used for transporting people or for communicating, such as with a smartphone, or for propulsion in space, and so on and so forth. So engineering design is a very important part of all engineering disciplines. In mechanical engineering, a big role is played by virtual design and simulation, because nowadays students are being trained to use very sophisticated tools, including CAD tools, but much more than CAD tools as well, in order to simulate structures and their failure. There's extensive experimental work with hands-on projects. I will give you a lot of examples of these hands-on projects. And lastly, to keep in mind that engineering is a very, what I would call a very social discipline. No engineer works all by themselves, but instead there's extensive teamwork, which of course brings up the issue of to have effective teamwork, you need to have effective means of communication, both in writing and in speaking. Okay. Now, I've listed here a list. So this is about 18 years old, from 2003. The National Academy of Engineering has listed here the greatest engineering achievements from the 20th century. And this gives you an idea of what engineering technology has accomplished for humanity. And I have listed here in red topics which have extensive mechanical engineering contributions. And this is a good way for essentially as a point of reference for identifying where mechanical engineers in the past have made huge contributions. For example, in designing and implementing electrification, designing propulsion in cars, airplanes, water supply and distribution, you see for agricultural mechanization, air conditioning and refrigeration, designing of highways, spacecraft, household appliances, health technologies, petroleum and petrochemical technologies involving all types of fluids, nuclear technologies, high performance materials. So you see from here that you can easily see the broad range of contributions that mechanical engineering has made in the 20th century. So 20th century is the last century. So this is essentially what has been accomplished. But perhaps even more important is to look at the challenges in engineering, and specifically mechanical engineering technologies for the 21st century. So that will be coming up in the later part of this presentation. So just to see some of the ways in which mechanical engineers approach mechanical design. One identifies what I would call optimum performance indices. And one, in optimum performance indices, one has to play around with technical performance. In other words, how well will a given design actually do? The cost of the is expensive, inexpensive, the environmental effect of that, and perhaps a longer term question. In other words, is this product sustainable? And is the technology therefore sustainable? And the way we do this is to identify different indices which need to be optimized or maximized in some sense, so as to improve this performance, to make this performance essentially optimal. For example, we can have a technical index, what I call here P-Tech, or we can design a structure for optimum performance per dollar spent in using or in implementing this device, where cost now comes into the picture, or design for the environment, or design for sustainability. And when we're looking for a design for the environment, we're looking at effects that can be done or undone on a relatively short time scale, 5 to 10 years. On the other hand, when we're looking at design for longer term sustainability, we're looking at a much longer time horizon on the order of 10 to 100 years. And then we can look at the effect, for example, of global warming, greenhouse gases, and so on and so forth. Therefore, the point I'm making from here is that we can identify different metrics, different indices, if you like, that need to be optimized for different types of design requirements. One important point I want to make is that engineering, again, I think is a very social type of discipline. In addition to the engineering design topics I just described, technical performance, cost, environmental effects, sustainability, there are some very important ethical questions that all engineers must actually deal. For example, there's a very strict code of ethics, professional engineering ethics. And this is the sort of topic that I will always ask high school students or first year students, true or false. And the statement below is that engineers in the fulfillment of their professional duties must carefully consider the safety, health, and welfare of the public. And this statement is actually false, because carefully considering the safety, health, and welfare is not good enough. Carefully considering something doesn't mean that we have given the most important aspect in the design in the safety, health, and welfare of the public. Therefore, the true version of this statement is that engineers shall hold paramount the safety, health, and welfare of the public. Again, there's a very important emphasis on the ethical responsibility of the engineer, because what we design and what we put in practice affects people's safety, health, and welfare. Now, again, as I said, there's this list of fundamental ethical tenets that all engineers must live by, and we try to introduce students at the undergraduate level so that they know what to expect when they're actually practicing engineers. Therefore, as you'll see again from canon number 1, that the correct statement is that engineers shall hold paramount the safety, health, and welfare of the public. Not carefully consider. Carefully considering something doesn't mean that you will actually implement it. It must be paramount. So some applications of mechanical engineering education and technology and research is in designing energy efficient homes, and of course the design of essentially insulating materials. Insulation is a big part of engineering technologies. So there you go. This is something that we all understand, that I can have a house that spends a lot of electricity or gas to be heated, or I can have a well insulated, therefore an energy efficient home. Again, just to give you an idea of what the notion of energy efficiency implies, I have listed here the cost of electricity use for operating a household refrigerator. And you will see that in going from the early 70s to the early 2000s, over a period of about 30 or 35 years, you will see how significantly the cost of electricity has actually dropped, simply because engineers can now design and produce much more energy efficient refrigerators. Understand that the production and transfer of power involves very sophisticated technology, and I'm listing from here 2 examples of essentially topics that we discuss very extensively in undergraduate class in mechanical engineering. As a matter of fact, these 2 topics are discussed in the 2nd year undergraduate course in engineering thermodynamics. For example, on one hand, on the left, we have what I would call a traditional coal-fired steam plant, where the efficiency, for many technical reasons, cannot really exceed 30 to 35%, no matter how hard engineers can actually try. This is an inherent limitation of the traditional coal-fired, water-based power plant. On the other hand, if instead of using water as the working fluid, if instead you use gas, such as air, you can achieve almost twice as high an efficiency, up to 60%. And the reason for this is that in a gas turbine, we can operate at much higher temperatures. Therefore, operating at lower temperatures or operating at higher temperatures plays a very big role on how efficient engineering designs when it comes to power production may actually be. Again, these are 2 examples that we discuss in great detail in the 2nd year course in engineering thermodynamics. Another example is using very sophisticated software to design different structural components that go into all kinds of technologies. So here's an example of a valve train lifter used in a piston and in a car engine, and you will see the CAD drawing here on the left. The CAD
We're having some technical issues. It should be coming right back. Dr. Lambropoulos. Except for those watching right now, we're having just a bit of technical problems. I'm sure Dr. Lambropoulos will be back. during this time, we can update you on the future full spectrum series that will be coming up. We will have, like I said in the beginning of the broadcasts, we will have Dr. Sripati Pai come in for computer science on November 5th. Also, we have Creating Your Own Major with Dean Lomibao coming up. So we're both excited about these two presentations. After that, I can go a little bit further. We have Electrical and Computer Engineering with Dr. Thomas Howard, who works on a lot of the robotics projects for the Hajim School of Engineering and Applied Sciences. So a lot of prospective families are interested in this because they are attracted to robotics and the idea of its implementation in the different forms that we have, whether it be computer science or whether it be electrical and computer engineering. And finally, we have data science with Dr. Ajay Anand, which it has been becoming more and more popular, the idea of using big data to understand aspects of our society that we're trying to improve, which is aligned with our grand challenges, but also those that can be a little bit more specialized. So Dr. Lambropoulos is coming back. We lost you for a moment there, Dr. Lambropoulos. Let's see if we can get him going. Technical difficulties are a hallmark of Zoom, so we're all prepared to be able to pivot for that.
So let me go back into sharing my screen. Can you hear me? Or is this my connection that is problematic on this side?
Yeah, yeah, we can wait for that. That's the best part about this, is that people can see that they're, you know, we're trying to keep this as genuine as possible.
Okay.
No flaws and all. So yeah, let me add you.
So let me go back into this. So we're just describing here the idea of using essentially sophisticated optimization packages to take a square block of material and remove material where the material is redundant and concentrate the material where the material is of greatest use. Therefore, we optimize the use of available material. We save a lot on material cost, and optimize the structural integrity of this structure. Here's another example of of another application. This is an example of nonlinear dynamics structural application, where we have a valve train assembly. On the left-hand side is the CAD model. On the middle is a diagram of perhaps an acceleration as a function of time. But perhaps most importantly, on the right-hand side, you will see again this finite element discretization of the CAD model, which will allow us to find the dynamic stresses and the dynamic deflections and deformations of the structure in a virtual simulation of its operation. And here's another example to show you how engineers design in a cycle. Again, you will see here on the left-hand side, there's a valve train assembly. It has been discretized into finite elements. The finite element simulation gives that around a hole drilled on the surface, one might expect stress concentrations. On the bottom right, you will see that in red, where the stress concentrations are expected. And when this structure is actually tested in an actual engineering laboratory, you will see that from the surface of that hole, two circumferential cracks evolve. Therefore, we use a virtual design to simulate failure and predict failure. And of course, at some point, these predictions are tested and confirmed in a laboratory. One other important question is to identify optimal material usage. And this is a very common example, because we're asking, for example, here a question in terms of environmental, in terms of sustainability effects. We can design a whole bunch of different containers to contain liquid. For example, have a glass container to contain, for example, an expensive liquid such as wine or champagne, a polyethylene container for milk, a PET container for a soda, an aluminum can. Are there other materials that can be used for designing essentially containers, such as will actually reduce the energy used in making this material? And perhaps more importantly, to ensure that there's less CO2 production in these different type of very consumer-oriented technologies. And so, for example, we do here a systematic study where for the different types of materials, polyethylene terephthalate, polyethylene, glass, aluminum, or even say steel, how much, what the weight for each container per liter of fluid contained is, the energy required to produce it, how much CO2, carbon dioxide is produced per liter of contained fluid, and finally, the cost of how much it costs to produce the container per liter, for example, of contained fluid. And the point I'm making from here is that sometimes solutions might actually surprise us. For example, you'll see from here that when it comes to costs per container, polyethylene is very inexpensive, but so is steel. But we don't typically think of steel as being a material being used to contain fluids. But this is a possible application. Therefore, we cannot exclude a priori a possibility unless we analyze it technically, and so on and so forth. Again, the cost of different engineering materials is very important. I have here the 4 broad classifications of engineering materials: metals and metallic alloys, ceramic, conductive materials, or plastics, if you like, and composites. And then you will see that on the vertical axis is the relative cost of materials, which can vary significantly. Of course, diamond is very expensive. Glasses and concrete, which are ceramic materials, are very inexpensive, and everything in between. Therefore, cost and performance come into play in selecting materials for engineering applications. Again, the notion that in mechanical engineering, we don't simply design something and forget about it, but instead we have to think about essentially extracting resources from the earth, producing the material, manufacturing the material and its components, using the material, and then essentially disposing the used or the exhausted or the deteriorated kind of material. Therefore, there's this cycle of material usage, and we must take this into account in predicting how different structures and different applications and different designs will have longer term effects, especially at the sustainability level. Something that is very fundamental in mechanical engineering is understanding how structures deform. And this material that could be easily included in a second year mechanics of materials course that we're teaching to our undergraduate students, namely the difference between tension, bending, torsion, and compression of engineering structures. It turns out that if we understand tension, bending, torsion, and compression, by combining these 4 modes of deformation, we can understand very complicated structures and how they deform. And in understanding the material contribution, we have a given material to make an engineering component. Then there's a macroscopic shape. So I combine the material with its material properties with a macroscopic shape in order to give me the engineering design that we actually desire. And you can see from here that the material can be and the shape can be monolithic, or it can be in this foam type of cellular kind of structure with big cells or with small cells. Therefore, these are options which have been optimized for this specific technical metrics and their optimization. Again, to go back into this notion of engineering design, we can design structures which are light and stiff. So this will be the kind of structure we'll call aerospace applications. A structure will be light and strong, also aerospace. A structure will be economic and stiff. Now, economic and stiff, we're looking at perhaps household applications such as cutting utensils, machining tools, and so on and so forth. Therefore, all of these different aspects of performance are quantified by combining different aspects of materials in engineering designs. Again, something that is a little bit more challenging to quantify, how to design materials which are environmental and stiff or sustainable and stiff. And again, we need to combine a whole bunch of different metrics in designing and selecting the optimum material for a given application. So here I would like to go into some examples of what kind of projects our students in mechanical engineering at the U of R are exposed to. And I will start from younger projects in the second year, and I will conclude with projects in the third year and the fourth year. So for example, so this is a typical second year design project in the course on engineering thermodynamics to design a small water-based power plant as a backup for a small hospital. So in case there's a blackout and electricity is not available, a backup essentially generator to create power for a small application. Again, considerations range from technical, safety, environmental, and financial, economic implications. Another example is to redesign essentially a cooling system, if you like, a refrigeration system, to operate using refrigerant R744, which is essentially a CO2, instead of the much more harmful fluorocarbon refrigerants that will R134A. Again, this is a very interesting kind of technology, because if I can extract CO2 from the atmosphere and I can make it into a liquid form, I can use it as a refrigerant, which is a much better option than using the much more harmful fluorocarbon refrigerants, which have been used in many years. And you see from here that now the important metric here is the global warming potential, which is 1 for CO2. CO2 is the baseline, whereas for these nasty refrigerants, the global warming potential is more than 1,000 times higher. So again, how do you take essentially a refrigeration system and redesign it just to operate with a much more environmentally benign CO2 refrigerant as compared to the nastier R134A refrigerant? These are second year projects. Again, understanding the implications of the steam or water-based power plant. I've listed from here the different engineering components that go into this power plant. There's a turbine, there's a condenser, there's a pump, there's a heater or a boiler. So understanding how these components operate is a very important capability that we teach to our second year students. And likewise, to take the sort of the opposite situation, rather than looking at the power plant, we can look at refrigeration or heat pumps or essentially air conditioning systems, and identify what is the benefit and what is the cost, which naturally leads to the concept of efficiency. So again, this is an example of a refrigeration system. And again, each of these components, we teach their engineering analysis to our second year students. Now we'll move into a little bit more, later in the curriculum, engineering projects. So this is a project on the in the third year course on material science. So for example, select the optimal material for constructing a large telescope mirror such that it operates over a range of temperatures, resistant to vibration, and so on and so forth. And choices are among glasses, ceramics, metals, and composites. So this is now the project where we take a mechanical performance of an engineering component. In this case, it's a large telescope mirror. And we want to select the ideal material so that some specifications are met. It should be able to operate through a range of temperatures, say very hot temperature to very cold temperature without the material actually cracking. It should not vibrate because then this would deteriorate its optical performance, and so on and so forth. This is a typical third year design project in the heat transfer course, which essentially was to design the optimal cooling schedule for a large, expensive optical glass that we call phosphate glass, so that it can be cooled from a high temperature to room temperature without breaking. So this, the driver for this project is essentially to shorten the time required to cool this component. And again, this is a very important, very expensive component. It costs about $100,000. So I cannot afford to break a couple of these. Therefore, I can cool this over a matter of 1 hour or 3 hours or 10 hours or 30 hours. And of course, this makes a very big difference. So here, there are very important concepts of heat transfer involved in this design project. And something that we also discuss in the third year courses is how to understand climate change and global warming. And we teach our students, for example, this global energy budget as a typical example of a heat transfer system operating between the atmosphere and the earth, with this heating and cooling mechanisms based on UV light, essentially sunlight, and infrared, essentially heat being emitted from the surface of the earth. So we look at global warming and climate change from the point of view of heat transfer systems. This is essentially heat exchanger. So when we teach heat exchangers in the third year course on heat transfer, we teach, as one example, this global energy budget as an example of heat transfer. Some typical fourth year design projects. This is in the advanced heat power course, which students take in their fourth year, to simulate a reactivity accident in a nuclear reactor. God forbid that such a thing will happen, but we must be prepared for every eventuality. Therefore, how do we simulate an accident in a nuclear reactor? Another example is to design a turbocharged engine for an aircraft. Now, these projects clearly are much more involved, much more complicated. So these projects will typically take 2 to 3 months to actually perform the overall, to complete the overall design project. In the advanced mechanical design fourth year courses, these are projects that students have worked with in the last few years. One is to design a wind turbine for a third world country by using only off-the-shelf components, and would cost only less than $10,000. This is a challenging project because there are some significant limitations. You cannot have one-of-a-kind type of components. There must be off-the-shelf components. It must be relatively inexpensive. Another example, and I will show you a picture of this in just a minute, design the support structure for a very thin, deformable mirror that will have an adjustable focal length, so that the mirror would operate by using sunlight. And the idea is that you would concentrate sunlight to a specific focal point. So essentially, I can convert light power, if you like, into thermal power. And so, and these are some examples of the simulations of how this very thin, flexible mirror can vibrate and shake in this what we call breathing mode, where the whole mirror moves almost like expanding, almost like a balloon, or in another mode, in another vibration mode, where there's sort of two valleys and a hill in between. So we call this the first mode of vibration. This will be a second mode of vibration. Another example of a fourth year design project is to build a prototype of a trefoil mirror. So trefoil mirror is something that looks like a highly curved potato chip. You'll see from here on the left, there's the CAD design of the trefoil mirror. It has 3 high points. That's why it's called trefoil. And the mirror was 3D printed by using 3D printers at U of R, and then it was coated by gold, and then it was actually measured. So you'll see from here how we go from CAD design to 3D printing, coating, and then measuring the performance and the uniformity of this mirror. Again, this is something that is an important capability, because it shows how 3D printing plays a very important role in engineering technologies. Here's another design in a fourth year advanced mechanical design project. This is actually a project that I actually sponsored. I mentored this project. The idea is to design a fixture so that one can hold and test the thin glass plates that are used to cover smartphones. This very thin glass, extremely thin. So how do you actually test this kind of glass? So the team first did a CAD of the testing device, then they built a prototype, and then they actually observed that the importance of chips on the surface, on the face of this glass. So again, the point I'm making from here is that we go from a CAD concept to an actual prototype to actual testing. Something that U of R is very good at is that U of R, there's extensive research and education on alternative and renewable energy. And I've listed here in green research areas which are very prominent at the University of Rochester, such as solar photovoltaic power, fuel cells, biomass conversion, fusion, and hydrogen production. So fusion, as you may know, is a very important capability. It's taking place, massive amount of research at the Laboratory for Laser Energetics, in which, by the way, many mechanical engineering undergraduates have done internships over the years, and many of these interns eventually are employed by and work at LLE. Something that an important question that I will simply pose here, but I don't want to spend too much time in discussing its implementation, its implications, is what do we do with CO2? What do we do with carbon dioxide? We put a lot of carbon dioxide. Therefore, the notion of carbon sequestration. How do I take carbon and simply remove it from the atmosphere and store it safely so it doesn't re-enter the atmosphere is a very important question. So I will just pose this question as an important technology that involves mechanical engineering, chemical engineering, and geology. Extensive projects and project work in the mechanical engineering program, experimentation. You will see from here students working on different projects and making presentations. Communication, both in oral and written form, is extremely important. Therefore, we train the students extensively in writing technical reports, making technical proposals, defending those proposals, and submitting final technical reports, and then also making oral presentation of these final reports. That's how engineers work in the real world. Communication is an essential skill because engineering fundamentally is a social practice. Again, simulation, manufacturing, testing of prototypes, and you will see again, here are some examples of structures that students have built, that students have actually built in the past. And I can answer more questions about this, but I would just want to emphasize that in this example, it's the design of balsa structures. Some high school students have done this kind of exercise, but the task here is to actually simulate failure of these balsa wood structures on the computer. And then success is not having a good design. Success is when the prototype is tested and agrees with the simulation of the same structure. So much more sophisticated view of engineering design. You build something through a virtual design process, and then you test it. So the agreement between the virtual reality and actual reality is what matters. A lot of student-led kind of projects, the mini Baja competition that students have been doing for quite many years. This is something that U of R and both mechanical engineering and other engineering departments have invested a lot of resources to give the tools and the machine shop skills to the students to design the mini Baja cart. Every year there are a couple of national and local competitions, and students love this kind of experience. Another similar project is Solar Splash, where the idea is to design, again, these are all student-led activities. The idea is to design a photovoltaic driven boat, and then take this boat and actually compete. So students build hulls, they optimize the hulls, they optimize the power of how they convert by using solar cells, sunlight into mechanical power, and so on and so forth. Again, this is an example of a very multidisciplinary student-led kind of project. What do our students do when they graduate? Typically, 1/3 of them go into graduate school, either MS or for the MS or the PhD. About 2/3 work in industry, but there are other opportunities that mechanical engineering students can pursue. For example, business school, a lot of the students eventually or immediately will go into business school. Some of them will go into law school, which is a very lucrative kind of occupation, especially in the area of patent law and intellectual property. The increasing role of the mechanical engineers as an entrepreneur, namely, how do you design and produce and demonstrate new structures to solve a specific problem. In terms of more practical considerations, with a BS in mechanical engineering, typical starting salaries is 55 to 75K. For students who go on and get in with a master's degree, there's a significantly higher salary that the students actually end up with. So let me go back to sort of summarizing where mechanical engineers have made huge contributions and where mechanical engineers are expected to make huge contributions in the 21st century. So I started with this slide when we started this presentation. These are the greatest engineering achievements in the 20th century. So this is in the last century: electrification, cars, airplanes, computers, telephones, and so on and so forth. The point I want to make from here is that by the end of the 20th century, everybody is familiar with all these technologies. But the point is that 100 years earlier, at the beginning of the 20th century, in 1903, how many people could think of airplanes, electronics, radio and television, computers, telephones, spacecraft, internet, imaging, and so on and so forth? Therefore, the idea is that over a period of 100 years, engineers, and specifically mechanical engineers, have made huge contributions in technology that we use currently. But perhaps for younger students, it's not so much what mechanical engineering has done in the last century, but instead what mechanical engineering is expected to contribute in the 21st century. And I've listed here the greatest engineering challenges published by the National Academy of Engineering about 15 years ago, 13 years ago or so. And now you will realize that in these big engineering challenges, it's more difficult to distinguish what's mechanical engineering, what's electrical engineering, what's chemical engineering, what's biomedical, what's computer engineering. But now the problems are much more driven by human needs. And for example, the first task, the first challenge, to make solar energy economical, this involves chemistry, physics, material science, mechanical, chemical engineering, possibly biomedical engineering. So the point I'm making from here is that the important challenging problems in engineering technology for the 21st century, for the century of students who are now beginning their college, their university careers, much more interdisciplinary, much more challenging. And my expectation is that as we address these new problems, the groups of people who will be addressing these new problems will not be singly identified as mechanical engineers or electrical engineers or biomedical engineers or optical engineers or chemical engineers. But now we need this combined skill sets to address these problems simply because they're much more challenging. So that's basically the presentation that I have in mind. Thank you all very much for attending, and we'll stop at this point.
Yeah, thank you for that. I feel like we covered so much ground between where we've been and where we're going. I think that being able to have read a lot of entrance applications for students who are interested in mechanical engineering, they cite auto or aerospace or structural engineering because it's what they're typically exposed to in the greatest amount or first. Can you tell me, besides those three, what do a lot of the students not know about in terms of areas of engineering that they get attracted to, and what is one of the more popular ones that students will seek outside of those three?
In my opinion, the most important skill that all engineering students get is problem solving. So problem solving skills is something that is not learned in 1 week or in 1 month or in 1 semester or in 1 year, but you need to develop this through the engineering curriculum. You develop your brain starts to think about taking a large, challenging problem, breaking it into smaller pieces, solve its smaller piece separately, and then synthesize the overall solution. So this is something that engineers do, but it is not a kind of skill that is learned, as I said, over a short period of time. The other important point I want to emphasize is that the importance of materials. Everything that we touch, everything that we see is made out of materials. And the materials can be taken advantage of, if you like, at the nanoscopic level, or they can be taken advantage of at the macroscopic level. I can hold a glass, I can hold my computer, I know what my car looks like, I know what the pavement or an aircraft actually looks like, and so on and so forth. But to optimize those materials, I need to understand their properties at the nanometer level. Therefore, this connection between engineering application at the macroscopic or human level and understanding and optimizing and improving at the nanoscopic level is something, again, it's one of those skills that you need to develop a certain way of thinking about these problems. Again, in energy applications, I mentioned that at the U of R, alternative energy, specifically energy from fusion, is a very important technology. But to understand and improve and make fusion power economical, we need to understand what happens at the microscopic level. Therefore, rather than be looking at things that only we can touch with our hands, understand the connection between the engineering up at the human level, but all the way down to the, let's say, almost atomic, not quite atomic, but close to atomic level, at the nanoscopic level, and everything in between. So we need courses in chemistry, in physics, in many aspects of engineering, mechanical or engineering design. So these are skills that cannot be learned in a short period of time. You need to train your brain to think in that specific direction. But as you said, certainly aerospace type of applications, alternative energy type of applications, cars and automotive type of applications, but also the area of materials and understanding the production of power, the production of energy at the microscopic level. These are important things in mechanical engineering.
So you alluded to a little bit of what the problem solving looks like with the small groups and the projects, which I think is great, because a lot of the time in perspective, and even first year students, just trying to think of what it looks like. Can you talk a little bit about problem solving and how much is it done on your own? How much is it done in groups? Like, what does problem solving look like ultimately?
So problem solving at a small scale might involve, for example, so we have a homework problem. So my friend Jack and my friend Mary and I will get together and we'll solve a problem. It's a challenging problem. It's group work. Each one will contribute some idea and hopefully we'll solve the problem maybe in 1 hour. But in mechanical engineering design, teamwork is much more extensive in the sense that you can work with the project, say, for 3 or 4 months. So this means that you need to follow a certain timeline. You need to have specific milestones. You need to have specific outcomes. So you can actually document how progress towards solving the project is actually carried out. The most important thing, I think, is that especially to begin this kind of teamwork is brainstorming. So in brainstorming, where nobody can say this is the best solution because I say so, but instead there's a brainstorming where all suggestions are written, on a blackboard or on a whiteboard or on a piece of paper. And then we can start analyzing by using our engineering skills, the implications of these brainstorming, brain products, ideas, if you like. The most important thing is to ensure that different team members have responsibility for different parts of the overall project, that they all talk to each other almost daily, and that they coordinate this work so that no part of the work is actually being left behind because somebody may be, maybe too busy. So in engineering teamwork, coordination and communication among the team members is extremely important, especially for the larger projects, which cannot be done over a matter of 1 hour or 1 day. For the larger projects, you need to break it down into its components, with each components having deliverables, outcomes, and milestones. So in the grown-up world of professional life, I need to know what is it that I'm trying to accomplish. I need to define an outcome, and how will I know that my outcome has been successful? So I need to have a milestone that if I attain this milestone, I know that I can move on to the next phase of that project. So project coordination and communication among the team members is really critical, especially for the larger projects.
So I also wanted to potentially bring into the discussion, we also have Associate Dean Paul Funkenbush, who is a professor of mechanical engineering and of material science. So I guess my question is for both of you. We've had the privilege of having Ed Hajim be able to give his speech and talking about his life. One of the things I really love about his speech is he talks about hard work, and he talks about, finding people to work with, but he also talks about catching your wave, right? So jumping onto something that you think is going to be successful. What do either of you or both of you think is the next big wave in mechanical engineering?
John knows my answer, I think, so I'll let him go first. Don't steal my answer.
Yeah, in my opinion, I would say I would give a two-part answer. One is new materials. I don't want to specify what those materials will be. I can, if you ask me to, but new materials. And secondly, taking advantage of clean energy. In other words, what is clean energy, and how do we implement it, but at the human scale, not at the lab scale, but rather how do we make power plants that operate without producing CO2 and without using exhaustible natural resources. So materials and clean energy is what I would define as the big waves for the future.
So my answer, and this is my 21st century answer. So since about 2000, I've been saying this. I think the wave for the century is biology. So biological connections for any kind of engineering. So not just mechanical, but it's becoming more and more a question of adapting it to the human body, building things, custom building things for individual humans. I really think that's a connection which applies just completely across engineering.
Yeah, a lot of it seems to have pointed to the interdisciplinary nature of this. And one of the things that I think is really great about our curriculum is that you have the opportunity to potentially change your mind if you've gone in one direction, but understand and see that, maybe I'm more, maybe I thought I was biomedical engineering, but I'm more closer to the parts of instrumentation that I can identify, and how do I then switch? So it's good to know that we've built it so you can do that here. I guess it's to focus a little bit more on the materials. What type of student is typically attracted to material science then?
I actually, both Professor Funkenbush and I, we both are faculty members in the material science program, and we have worked in material science for many years, from different perspectives. But I would say that materials and the need for materials is prevalent. Therefore, I don't want to think about the importance of materials for mechanical engineers, but the importance of materials for biomedical, optical, chemical engineers, electrical engineers. Everything, not quite everything, but a large part of the world around us is made out of materials, and the materials we make have increasingly more stringent requirements. So now, which student is attracted to this field? I would say a student who likes to think about small things. In other words, you must be comfortable with the idea of atoms, must be comfortable with the idea of molecules. This involves some preparation in chemistry, some basic preparation in physics. But the University of Rochester does not have an undergraduate program in an undergraduate degree in material science. But we have a minor in material science, and we have both a master's in material science and a doctoral program in material science. Therefore, for all engineering students, including, by the way, students from chemistry, biology, or physics, or geology, earth and environmental sciences, those students would be very well prepared in looking at more opportunities in material science at U of R?
I'll give again a contrasting answer. I would say a student who's interested in kind of the how. So why, or the how or the why. So why is the steel so high strength? Why does the semiconductor work the way it works? And the answer to all those questions is really at the atomic level. And so in order to understand, why steel is strong or why a semiconductor behaves the way it does, you have to understand things at the atomic level. And so students who are interested in finding out that why tend to be attracted to material science in my background. I'll add, I mean, John actually teaches this class, but all mechanical engineering students take a course in material science. So even though you don't get a degree in it, it's really important to mechanical engineering, and our students do get that course from the faculty.
I like hearing that there are slightly different perspectives, only because that lends to the whole credence of this is all problem solving, right? I work primarily with underrepresented students, as you know, and one of the conversations that we have is that, it's not that we want just a diverse looking group within a lab, but we want a diversity of experience, right? A diversity of how you've learned to problem solve and your life story and what it took you to get here. Ultimately, if it's different from the person standing next to you, you might approach a problem in a different way. With that, part of what the biggest fear for a lot of the incoming students and prospective students is failure. And we have asked all of the participants of this, is that what does failure look like? How is it a part of mechanical engineering? And ultimately, how does that lead to success?
That's a challenging question, but I would say that nobody is trained fully to be an engineering major at U of R. You need to start from a certain, so you need some background. So for example, you need to develop some mathematical skills. You need to develop some physics skills. You develop some basic writing and communication skills. So these foundational courses are part of every engineering major at U of R, and I suspect of every engineering major in every university in the world. So we don't throw students into advanced courses from the get-go, but we train the students to think mathematically, to think quantitatively, to develop a good physical intuition through their natural science courses. And the engineering courses, every engineering course, of course, uses the same physical principles. So when we write quantum mechanics or F equals ma or different types of equations, these are, we don't, in engineering, we don't violate physical principles. We use physical principles to take advantage of these physical principles to create something that solves human problems. So I guess failure is the sort of thing that sometimes students will say, oh, I have to take math, but I want to be an engineering student. Maybe I don't like math. But the basic idea is to understand that these foundational skills are critical in developing highly performing students in their second, third, and fourth years. That's why a lot of the emphasis on the U of R undergraduate college is to make sure that students do well in their math, physics, chemistry, biology courses, I think.
Now, I guess we have time for the one last question we have is for prospective students or even students who are just changing after the first semester into mechanical, what is something that they can read or review or look at? A lot of times we'll have parents asking, like, what can I do to make sure that my kid is really interested in this? What is some of your advice for them to do, or something that they can do?
What I would suggest is something that's very pedantic. It's pedantic and boring. But I would say a good way to prepare for engineering is review at some high level. You don't have to go through every single, review your quantitative courses that you took in high school. Review your math, physics, chemistry, bio courses at a high level and see if you can develop those connecting threads between the different courses, those common words, those common concepts, atoms, molecules, cells, these concepts are so foundational. And the more familiar a student is entering at the university in the STEM field with these concepts, the easier it is to delve into greater detail. So this answer is kind of boring, go back and review your STEM courses that you did in high school. But I think this is a good way to actually, there are many books, very sort of what I call like low-level books that talk about engineering technologies, but any specific book is quite detailed. So by necessity, it would not cover the broad picture. So for the broad picture, get familiar and refamiliarize yourself again with things in the STEM fields that you've learned either in your first year at U of R or in your high school education.
Well, go ahead.
I'll just pop in and say one other thing you can do is that if you're a student or if you like to figure out how things work, right? And it doesn't have to be really complicated things, but just even simple things. So for example, I was driving along one time with my kids and we saw a stop sign and the stop sign had holes drilled in it. And so the question was, well, why does the stop sign have holes drilled in it, right? That level of curiosity and being able to figure out why the stop sign has holes drilled in it is actually a good indicator that maybe of a budding engineer there.
Well, excellent. That can also be a function of if you find out why stop signs have holes drilled in them, please put it in the messages for this broadcast and we will get you a prize. It's a perfect setup. We didn't even set that up, and I think it's a perfect segue. So Dr. Lambropoulos, we're at time right now. I wanted to thank you for coming in and doing this. It is very helpful for people to understand the number of applications that this can have in the different directions that someone in the field can go, because they'll come to us and they'll just think, okay, I'm interested in mechanical engineering, but I'm not 100% sure what that is or what I know what to do. And it's okay, right? There's a way and there's a way process to take this through. So we're really grateful that you're able to come and shed light on that. We will be back next Friday. We're off this Friday on November 5th with computer science with Dr. Sripati Pai from 2 to 3. Thank you again for being here, and we appreciate all of you watching the videos and posting comments, and we will see you next week.
Great. Thank you, Nick.
Yeah.